All right, the next timer that we want to talk about is going to be the timer that we employ when we lose a prefix in our routing table. Because what's going to happen is in our topology, if we lose a prefix, if we lose reachability information to reach a destination, what's going to happen is we're going to immediately begin sending queries. These query packets are designed to contact our neighbors and say, hey, do you have another way to reach this prefix? I just lost mine. Now what we have to understand here is EIGRP in its early days was a pretty persnickety protocol, because what happened was that this relationship between our neighbors was problematic and poorly designed infrastructures. Now by poorly designed infrastructures, I mean where what happens is if our neighbor doesn't know about that prefix, what's going to happen is it's going to send queries to its neighbors, and then they'll send queries to their neighbors. And the issue is that until we receive a reply back, we're not going to be able to process any traffic for that particular prefix. So the idea here is that we would arrive at a state called SIA, or stuck inactive, where we're actively trying to find a particular destination. Now let's see if we can't demonstrate how this works in a normal operational config. And what we're going to do here is just highlight, first of all, the fact that, again, we're going to use a loopback on R1. That loopback will again be 11.11.0.0/24, where the prefix is going to end in .11. And once again, we have our topology set up to where we have our reachability both through R2 and R3 on R22. We can illustrate that quite easily by going to R22. And on the confines of R22, I can type show IP route 11.11.0.0.255.255.255.0, and I can see that I'm going to load share. And lastly, we'll just simply trace route it to 11.11.0.11, and we'll see that we're going to go through R3 and R2 to reach our destinations. Now, if I lose a prefix, we want to talk about that idea of, bear with me just one moment. We want to talk about that idea of our queries. Now, I can come up here and I can say debug EIGRP packet, and I just want to look at the output such that it's going to give me terse. I don't want all kinds of stuff. I just want to display all EIGRP packets except hellos. Since the hellos are going to be bouncing back and forth every 5 seconds by default here, what I want to do is I'm going to say terse. That's going to restrict my output. Now what we're going to find here is that the moment, let's say I come in here and I say config T, and I create a new interface. Let's say interface do show run include or run do show IP interface brief E assigned addresses. Let's create a loopback. Interface LO 100. IP address 172.16.11 or 22.222.222. We'll just keep the numbering sequence the same. And 255.255.255.0. Well, let's see here. Now, what ends up happening here is, let's take a look at what's going on. We got some output pretty quickly. So what we did is we in-queued an update. Now, why did we do that? Well, let's take a look at this. Do show run section router. Notice it's already set up to advertise that network. Now, by virtue of the fact that that command is there, the moment that I created that interface, we sent an update out notifying the rest of the topology of the fact that we have this IP address that we want to be able to reach. Let's look at it. So when we go through, what we actually see here, let's scroll back up to our updates. We have an update, and what we did is we in-queued it on 2/0 and 2/1, and then we sent that update out. Notice that update had a serial number assigned to it. Now what that did is that was how we informed all of the other devices about how to reach that prefix. Let's go to R1 and see if it's in the routing table. Show IP route for 172.16.222.0.255.255.255.0. And what we see here is we not only know about it, we're going to load share to reach it. Because remember, it's equal cost this way and this way from both the perspective of R22 and of R1. So now if I trace route to that destination, to 172.16.222.222, I'm going to go across Cat1 and Cat2. So I'm going to do my load sharing. Now what I want to do is I want to mess with this. So let's go back over to R22, interface LO0 or LO100. Let's shut this down and see what happens. Well, something happened. Let's take a look at this. Notice we sent a query. We sent a query out on serial 2/1 and serial 2/0. Now, oddly enough, this query is where our system says, hey, I just lost this prefix. It was in my routing table and now it's gone. So what I need to do is I need to know if anybody else knows how to reach it. Now, this is kind of dumb. This is one of the things that bothers me when it comes to EIGRP, because this prefix was actually in and on physically R22. So what ends up happening is it immediately sent that prefix, that request out, and we ran into this scenario where we sent the query. All right. So when we lose a prefix, irregardless if it's a native interface or a connected interface that's being run in EIGRP, EIGRP doesn't care. It's inside the table. So if a prefix exits the table, whatever the conditions, and I do not have a feasible successor, something that met the feasibility condition in my topology table, the system is automatically going to initiate a query. Let's look at another role here. So when we look at what's going on, let's see what happens if we can actually stimulate something else. So first of all, I'm going to say no shut, and I'm going to bring this interface back up. That should facilitate a update, which it did. Notice that we're sending updates. You know, we've got our acknowledgments, we've got reliable communication, but the main thing I want to point out here is we sent an update out. That update actually advertised, or was sent to, first of all, this neighbor and this neighbor, and it advertised the prefix that we just brought up. That's going to be that 172.16.222.222.222. So looking at that, now we're good to go. But what happens here? Let's go to interface S20. First of all, let's do this. Do show IP route, and I want to look at 11.11.0.11. Actually, I'll look at 0.255.255.255.0. And notice I'm going to load share. This is that loopback that we were talking about here on R1. And what I want to do is I'm going to kill one of these connections. So interface serial 2.0 shut. Now let's see what's going on here. Let's see, do we send out a query? Notice we immediately send out a query. Now this query is really interesting for us because the moment I kill that connection, I lost an entry in my routing table. Now let's modify this. Remember, we were playing around with delay. Now what I'm going to do is I'm going to go in here. First of all, I'm going to bring this interface back up. And I'm going to say no shut. That's going to force an update. Because remember, that's in our routing table. The moment a prefix exits our routing table, we are going to query for it. But what I'm going to do is I'm going to go to R2, and on the interface 03, E03, what I want to do is I'm going to change the delay. I'm going to take it from 1,000 microseconds to 2,000 microseconds, which we know means I'm going to have to enter 200 tens of microseconds. We're going to do that on that interface there. So let's go ahead, R2, config T, interface, and what am I going to do? I'm going to say E03, I'm going to say delay 200. So do show run, or do show interface, E03, pipe include DLY, and we'll see it's now 2,000 microseconds, where before it was 1,000 microseconds, which is what it's going to be by default. Now let's cut over to R22. Show IP route 11.11.0.0. And what am I going to see? I only see the entry here for 2/1, which goes to R3, 223.3. The .3 tells me that that's R3. And I'm not going to trace route. I'm not going to load balance during a trace route. So trace route 11.11.0.11. I'm going straight through R3 to Cat2 all the way to R1. Now, if I come up here and do show IP EIGRP topology and look specifically at 11.11.0.0/24, I'm still going to see both entries in my routing table. So I've got 0.1, which is the route that I am taking, because my feasible distance should be 21. Let's see, it's going to be 2,195,744. The second entry is not going to be used. Say, hold on one second here. What have I got going on here? Where am I? That's the prefix that I'm going to use. And then when I come down here, I'm not going to use this prefix. For some reason I highlighted the microseconds, I'm sorry. So that's what's going on. But the question is this scenario right here is going to mean that I have a prefix, show IP route. I only have one entry for 1101 in my routing table via serial 21. Now what I'm going to do is I'm going to kill this prefix. I'm going to go over to, let's see, 21 is going to take me to R3, config T, interface, serial 2, 1, and I'm going to shut this interface down. Now on the confines of R2, let's see, did I lose my connection? Oh, I went to the wrong device. We're not even using interface on R3. Sorry about that. I want to go to R3. Config T interface, serial 2.1, and I'm going to shut this interface down. Now notice something happened here. We went down to state changed. R22, notice this. On R22 it says we received an update. We have the acknowledgement. The link has come back up. We sent an update. We lost our peer. The peer came back up, became operational. But notice in this output, nowhere do we enqueue a queue. We're never seeing a query message. The reason being, show IP route, is the fact that what we have in the routing table for 11.11.0.0 is we already have another interface that we're going to be able to send our update out, and we do not need to be able to send a query because we have that other entry that was floating inside of our table, our topology table. So what that means is just illustrating the point that I tried to drive home earlier, and that is the moment that we lose a route from the routing table, if we have a feasible successor to replace the successor, the route that made it into the routing table, then what we're going to do is send a query. But in an event where we're load sharing and we have two successors, we lose one, we did not have a third one in the routing, in the topology table, therefore we had to send a query. This gives us the capability of being able to observe this. Also, what we're going to do is later on we're going to talk about a concept called a stub area, which is never going to be transit for any other traffic. It's only going to have its own prefixes. So what we can do is we can actually stop this idea of sending these queries. But my point here is that what we want to do is we want to understand what happens when we use this concept of being able to say we're going to send this query, but we're only going to wait a certain amount of time before we receive a reply, because in the old days, poorly designed EIGRP topologies could quite literally trash themselves when we lost links, because it would take too long for these updates to arrive and we would be stuck inactive. So we're actively trying to query for a particular prefix. So when we go in and we look at this, what we're going to do is that we're going to entertain this concept of a timer called an SIA timer, or an active timer. And the goal here is to realize that the active timer is going to define how long we're going to wait to receive a response to these queries before we just flush that prefix out and reconverge where we've just got some information missing out of our routing table. Now keep in mind, it used to be said that EIGRP querying has a window of 1, which means it's going to send a query and wait for the reply. If it doesn't receive the reply, it would, in the original times, in the early days, wait forever. So what ended up happening was we come up with this concept of a stuck inactive timer in order to be able to minimize or define a period in which we are going to wait and then make a decision. So let's take a look at that timer. So first, what we want to do is let's make the understanding or the realization that when we go in and we look at this concept of how we have these timers, what we want to do is we want to analyze what happens in or on the configuration. So if I want to change the timer, what I'm going to do is I'm going to go to my device, config T, and I'm going to say router EIGRP 10, And what I'm going to do is I'm going to say timers, and the timer that I want to set is going to be my active dash time. So active dash time, and then what I can do is I can come up here and I can say how long I'm going to wait in minutes in order for this to do its thing. Now let's go in and take a look at another command here. Do show IP protocols. Notice it tells me my active timer by default is 3 minutes. Now, there's another timer here called the non-stop forwarding aware timer. We'll talk about that later on. The timer that I'm indicating or looking at right now is going to be this idea of the active timer. Now, if I wanted to change that timer, active time from 3 minutes, I could change it to 1 minute. Now, notice that has not impacted or affected my neighbor adjacencies. Again, in the confines of EIGRP, these do not have to match. It is best practice to make sure or to have all of our timers match and be synchronized with regard to the fact that we're all going to be sending and expecting information in the same windows. But the main thing that I want you to realize here is that they do not have to match. So now what's ended up happening is I'm sending this information, and I'm going to wait for a reply to come back that's going to be a period of 60 seconds now instead of 3 minutes. So by default, the stuck and active timer is 3 minutes. We can change it to, virtually anything from 1 to 65,535 minutes. So again, that would be kind of extreme, but it's important for us to realize that we do have the capability of being able to manipulate this. And if you do manipulate it, I would highly recommend that you're going to do it on all of the devices in your infrastructure. However, if you're not told to do it everywhere, don't do it everywhere. If you're instructed in the context of the CCIE Routing and Switching version 5 lab to change it, go ahead and change it where and when they tell you to. So I will see you guys in the next presentation where we're going to start talking about that idea of stub areas I mentioned. I'll see you over there. Bye-bye.